when I was talking about the kinetic energy, or I don't know how you might want to write it like this, or EK, they all mean the same, right? It doesn't matter. Okay, so I was saying, I had said, you know, the only change is, who had asked me, I can't remember. Or, yeah, okay. She goes like that.
Don't point at me.
Someone like that.
No.
All right, so I said, we can't change mass, right? So, can't change it. And then I said acceleration, right? The formula doesn't really change, because what is acceleration?
Velocity.
Light.
No. Acceleration is what? How do you define it? It's the increase, it's the rate of change of velocity. So that's why I didn't change it, because when the electrons first come out, they are gaining velocity as they are approaching the target. So that's what I use the term acceleration. It's not changing the formula, okay? All right? Yeah? For example, okay, you have I don't know, on a table, you have a ball, okay? You have a baseball. As the ball is going down, being pulled by gravity, is changing the velocity, which is increasing. That's acceleration. And so that's exactly what happens here. So I use the term acceleration. That's what I was meaning to say. Okay, the formula doesn't change. Is that clear for everybody? Okay. Thank you for reminding me. Thank you. Yes? Mona? All good? Yeah. Okay, good. Didn't confuse anybody, did I? Hope not. Okay, so let's back to Radt430. Any questions of what we've been doing? Yes, don't ask me questions about the quiz. Don't ask me questions about if it is the quiz. You get it back.
No, it's not a quiz, but it was in the quiz, but I was.
It's not in the quiz, but it's in the quiz.
It's the line focusing principle. How you have two different angles. I'm not really understanding of those angles.
Okay. Anything else? I can go over that. No problem. Anybody else? No? Okay, so let's see. So what is the line focus principle? Anybody? Right. UNG part. The line focus principle. What is that?
Depending on the actual focus spot or the angle of the target.
The angle. Go ahead.
The size of the effective.
There you go.
focus spot
We'll change it. Okay. All right. And so that's the concept of the line focus principle. Is depending on the angle you have, that will change in the effective focal spot. All right. And let's see. Andres, what is the effective focal spot?
The effective focal spot is the photons coming from the target angle. So if you have more of an angle, it will be more of an effective focal spot. If you have less, it would be smaller.
Okay, good. And just think about it. Say, for example, if you have a mirror, okay, you put a flashlight to the mirror, okay? The more you angle that mirror, then the light that is reflected onto, say, the floor, okay, will be wider. But the less of an angle you have, and this is the flashlight, the less of an angle, the less reflection of light you'll have on the floor. I mean, you'll have reflection here, but we don't care about that. We care about the beam that is coming out. And so as you change the angle, you can play this at home. I mean, when you get home, you can put a mirror and put it and see how much of a reflection you get on the floor. And then as you change the angle, without changing the angle of the light, you'll see that you have less of an angle. So it's the same thing, okay? Same idea, same concept, okay? All right. And what did we say about the heel? What is the heel effect? And let's see, Natvo, what do you think? What is the heel effect?
more distortion on the cathode side than the anode side.
Okay, why is that? Why does it happen? Don't read it. Just show.
There's more X-ray going to the cathode side.
Why?
The angle?
Thank you.
Why?
Why?
Crazy?
Well, no, I was just, because of the angle, I think isn't
Now,
there.
now explain it to us. You spoke, we listen.
No, I'm saying that's the reason why there's distortion, because of the angle, right? Isn't it because it's hitting? high-
Distortion? What do you mean by distortion?
Well, on that part, I'm kind of confused because I don't understand, like, when you were talking about it last week, you were saying that if it hits higher, it takes longer.
Not only higher, but if it, but you're in the right track, okay? So, Nat Vo, let's see. She wasn't able to help you. So we go back to you. You agree with her, that's what you said. So tell me why you agree with her. Careful what we speak. Anybody? So heel effect.
Is it because depending where it hits on the target material, it could be it could go further into the anode and it'll be absorbed in sense and it'll go at a different angle, so it won't come out at the effective focal spot area. So it could go upwards and out through the target material, and or it could be projected through the effective focal spot.
Okay. How will you say it?
When it hits the target, it angles out, and the angles going towards the anode side are more likely to have more interactions and lose or change direction from, so that you're going to get less towards the anode side and more, because the ones going towards the cathode side have less in their way, and so they'll come
Yeah,
out.
so exactly. I mean, the way they put
Yeah,
it.
that's kind of.
Okay.
Yeah.
The way both of them put it, that's what it is. When you hit the angle here, it's easier for, okay, the photons being created to go this way. Those that are going this way, they have to go through more material. Okay? And so the effect of it, okay, the effect of all of this problem, because it is, I mean, think about it, is this a problem or not?
Yeah.
Yes.
It is a problem, right? And so the problem is that you're having more photons on the cathode side, okay, than on the anode side. That's, and it is a big deal. We don't see much of a big deal anymore, but when we had film, in some cases it could make a drastic difference. Okay? And as the tube gets older, it becomes more evident, and it becomes more of a problem. Okay, because literally what you have is on the anode side, you have a lighter image than on the cathode side. Okay? Now, this is something I threw at you there. I think I hinted at you last week. Could you use this to your advantage when you are doing, when you're doing x-rays? How can you use it to your advantage?
Of the body, like if you were doing, let's say, a pelvis, you would put the pelvis part of the body towards, I guess, where most of the x-rays from, so behind the side, and you put the least denser part.
Exactly. So you can take advantage of this, okay? And that's how it is. So it is a bad thing, but we have what we have, and so we have to make the best use of it, right? So that's what happens with the heel effect. I'll go over it again. I'll take a look at it one more time, so everybody is clear with that. It's an important concept because, you know, with all the fancy equipment we have, the core, okay, of an X-ray tube is that. And the same problems they had in the 1920s and 30s, we're still having it now. 100 years after, that has not been improved. Okay? The improvement is with computer systems, because you can tell the computer, ignore these numbers here and make them all get an average of all the numbers, which is exactly what happens. So that's why you don't see a difference. Someone had a
That was gonna ask. So they haven't solved this, they just fix it with the digital.
Exactly, with the digital system, what they do is they do an average. They take an average numerical value of all the density values, exposure values that you have within an X-ray image. They do an average, and that's what they present to us. Yeah,
How do you find in the housing the cathode side and the anode side?
say that again.
How do you find in the housing of the beam,
Uh-huh.
the cathode side and the anode side?
Good question. A lot of times they are marked, okay? Many times they are not. That one I think is marked. I think you see a negative and a positive somewhere there, I think is marked. A lot of times is not marked, okay? A lot of times there is a little mark where you can tell which is which. If they are not marked, you can assume that on your left side, you're gonna have the anode, and the cathode would be on your right side, okay? I have only seen one piece of equipment, and they got rid of it at the VA, and that was, I don't know, 10, 15 years ago, where for whatever reason, it was reversed. I don't know why, what was the intent of reversing the tube? I think it's because, this is me, this is what I came up with, that it was a large X-ray room, and you could be on either side of the tube. On either side, you could walk, and there was no wires. It was a nice tube, but for whatever reason, they had flipped them. That's been the only case. And so, are there other tubes like that? I'm sure there are. But the majority are left and right. So cathode, anode. Okay. With mammography, they do something very interesting. Imagine this is the cathode side. I want you to pay attention because it's going to be on your test. Okay. Not only that it's going to be on your test, it's important. Okay. So it's important. Imagine this is the cathode side and this is the anode side. So what they do in mammography is they flip, they go like this. Okay, they turn the tube in, and so you have the cathode side on the chest wall. Will it end up being the chest wall of the patient? Why? Because this is where you want the greater amount of X-rays, because this is the thicker part of the breast. So that's what they do. That makes sense? So this goes toward the chest wall. It's gonna be inside. So you see it here. So when they X-ray the patient, then the thick, where you have the greater number of X-rays will be towards the chest wall. That make sense? Okay. All right, so let's go back. It's been here all day. All right, so very quickly, let's go over, I think, from the answers I got in the body language of the rest of the group. I think you guys understand it, but let's make sure. See, when you guys get something, you go like this. But if you don't, you start looking down. Effective focal spot. Okay, so it's controlled by the actual focal spot size. So the line focus principle, okay, because of the angles we have, we end up with this problem, right? You end up having, changing the effective focal spot, okay? And so this will be controlled by the actual focal spot size, is how wide of an area do you have, okay? Follow me? Where the electrons are hitting the target, how wide is that area? That will affect the effective focal spot, right? But also the angle, target angle. And so this is what I'm trying to show you here with that first bullet I show you. See here, it's the same, it's exact, this is wide, this is larger. So the actual focal spot here, see, is, I don't know, one hand, here is, what, 5 fingers with my hand closed. And so this one is in a smaller surface area. This is why you have, okay, and a smaller effective focal spot here, okay, compared to this one, right? if in both cases you have the same angle. Okay? So in this example, I'm giving you 12 degrees, 12 degrees, okay? But what we're saying is this is a larger area, that's why you have a larger effective focal spot. Many X-ray tubes, this is the most common way that X-ray tubes are going to be built, having the same angle, okay? They still have two focal spots because they have two filaments. And so what they do is, remember when I was showing you the focusing cups, the larger filament will cover this area and the smaller filament will cover this area, okay? And so you end up with this. However, you can also have dual filaments and dual focal spots where you have two areas. Let me go back here, okay? Are we clear with this? In this example, you have one target, one angle. Okay, what is changing is the filament. The you have one large filament and one small filament. Okay. Yeah, and because of the large or small filament, you end up with this, either a large or smaller actual focal spot. Okay, that's one way that you can deal with this problem. Another way is to change in the angle. So you have one filament is possible, okay? And in this case, you're gonna have the same area, take a look, same area of actual focal spot, okay? But what they do is they can change the angle, okay? Now, they don't do that. That will be too expensive to have the target change in angle. So what they do is within the same target, you're gonna have something like this. You'll have these targets look kind of like this. So they are not really flat. They have a curvature, and then you have one area for the small focal spot, one area for the large focal spot. Okay, and so you have one angle here and one angle here, right? Because this is not straight; it's curved. Okay, somewhat curved, and so but the concept is the same. So you have, okay, yeah.
Sorry, you can finish that. I was gonna
Okay,
refer back
so
to
in
that.
both cases, you're gonna have the same area of the actual focal spot being exposed. So this area here and this area here. But how they reflect, okay, the X-rays on the effective focal spot is different, okay? So you have, for example, here, okay, what you'll have is those with a larger angle will have a wider or larger effective focal spot. Okay, here, with less angle, and a smaller effective focal spot. Okay? Let's see what else. So, which one do you think is more effective? They both have advantages and disadvantages. The greater advantage of having large actual focal spots is that you have a larger area where you can hit the electrons.
Mm-hmm.
And so there is better heat dissipation. With the previous slide where you have a smaller effective focal spot, it can get really hot. Okay. Yeah.
So my question was, for when it's the two different angles, there's two different spots
Yeah.
that you can hit.
Yeah.
For the other one where it's the same angle, is it just one spot and you change the filament size?
filament.
But it's still one spot
still
that
one
it's
spot.
hitting?
Yeah.
And that's like
They
two
could have
different
two.
spots. Okay.
They could have two, but it's the same angle
It's
throughout.
the same angle throughout.
Throughout the target here. So instead of having two different angles here,
It's one angle but
it's
with
just
different filament?
one angle, but
Yeah.
one area is here and one area is here.
So it's still two separate places you
Could be.
hit?
Could
Okay,
be.
or it could be one and you just
Yeah.
activate
I don't know
different
if you saw
filaments.
did you saw, I think on one of the targets I was showing you,
Uh-huh.
there was one area.
was
that
one.
There were two areas that were shiny,
Yeah,
only on one of them. The
Yeah.
other ones, it only had one.
yeah. Okay, I was just wondering if it was
Yeah.
two different spots. on
It's
the other one?
usually
Like small
two
and
different
large?
spots.
Okay. Okay.
Yeah.
Do the electrons hit outside of the focal spot? Like,
We're gonna talk about that too. Yeah, so the great majority of X-rays, remember, what is it that we are using to compress those electrons? The focusing cup, right? So it's not very effective. So you're doing that. The minute you turn the polarity of the focusing cup positive, okay, then they start going, okay? And so the second they leave the the filament, remember these are alike charges, all negative, right? The minute they go like whoop. Yeah, you only hold them in place here, but once they leave, they're whoop. Okay. So the majority will hit the focusing cups,
Focus box.
actual focal spot. All right, but some of them will end up hitting here, and that creates problems. Okay, and some of them, and that will lead me to my next concept that we'll take a look at today. Some of them, even though they hit here, they don't go through the window. Or they go through the window, but they don't go at the angle that you want it to. So you, for example, you want these guys to go like this, right? And they are all going this way. Once in a while you have, you know, a bad child that will come here and whoop, will go that way. Or it can go anywhere. It doesn't follow the direction of the rest of the beam.
Why can't they extend the focusing cup between, are these halfway between the anode and cathode?
To extend the distance here?
Like an extension of the focusing cup to.
Because many of these electrons are not gonna make it. Yeah, they start, because of the charges, like they're gonna start going everywhere. Yeah. But there are other ideas now. This is the most basic concept of X-ray 2 engineering, but there are other ideas now. Other ideas where they're using almost like a linear accelerator. They use tunnels to completely direct the electrons, so they are going nowhere. Very expensive tubes, very expensive. Some of the metal tubes are like that. Yeah. All right. Are we good now? Everybody? Gracie? Okay. Everybody else? Back there? Good? All right, good. So let's move on. All right, so the anode hill effect we talked about, and so what we're saying is, for example, those that are going this way, they just come out this way, but those going towards the anode side, they have to go through all of this metal, and many of them will get absorbed, and so they don't make it on the anode side. Therefore, you end up with less X-rays. By the way, this is kind of weird, the way he has it. I probably will, instead of putting percentages, I will just put numbers, so ignore the percentages, okay? Imagine this is only 75, this is only an idea, right? We're not gonna get 75 photons. I don't know, maybe we'll get 7.5 million? You can do that, I don't know. And here you're gonna get 100 million, and here you're gonna get 120 million. Not percentages, because this can be, 100% is the maximum you can have, right? So it's here, so you cannot have more than that. But anyway, so what this is saying is that, let's think as X-ray text. So this is gonna go lighter, darker, less dark, less dark, less dark, less dark, less dark, until you have a lighter area here. So you can do it by shades. So as you're moving to the right, as you're moving towards the cathode, your image will look darker and darker. Okay?
Is that the burn out image considered?
Say that again?
Burn out image on the
No,
edges of burn, that's different?
No, a burnout image it's a black image, it's a dark image. Okay? All right, let's move on to the next thing here. Off-focus radiation, okay? So this is, okay, so another name for off-focus radiation is extrafocal radiation. And it's composed of photons that were not produced at the focal spot. Okay? So, X-rays that were not produced at the focal spot. And they are undesirable, you don't want them, okay? But they exist. It's not, well, Once again, this idea is not 100% effective. And so increases the skin dose, it reduces image contrast, okay? It can image tissue that was not intended to be included, okay? So all of those problems. So let me look at something here. Give me 1 second. Okay, so let's go back here. All right, so Daniel was asking before, he was saying, okay, how about do you have any electrons that hit off the target? Yeah, and that's what it is. Extrafocal radiation, or all-focus radiation. And they create problems, okay? You don't want them, okay? And there are different techniques you can use to minimize it, but not to completely reduce it. You probably are not aware of extrafocal radiation. And by the way, this is not leakage radiation. What is leakage radiation?
It's coming from the tube housing.
It's coming from the tube housing. All focal radiation, okay, is coming from the window, but it doesn't follow the angle of the beam, okay? And therefore, you end up X-raying parts that were not intended to be X-rayed. They were not part on your light field. For example, you're doing, I don't know, nasal bones, or you're doing a lateral facial bones, right? Doing a lateral facial bones. Bing, take the X-ray, you have a collimation and you see your light, it looks nice and straight. But when you get the image, you get more than what you asked for. Have you noticed this? And especially it happens with DR too, but it becomes more obvious with imaging plates. When you process them, and as the image is coming out, have you noticed that it first shows you an image, and it has more stuff than what you intended, and then boom, boom, the computer cleans it for you, and you have nice collimation?
Yes.
Yeah.
So all that extra tissue was not intended, and it was exposed by off-focus radiation. Okay? So it's kind of like this. I think I have a picture here. Yeah, I have a picture here. So same thing. They're doing nasal bones or facial bones. All of this, see the shadow here, see the lips, see the nose? That was not intended. And it happens with many body parts. It happens with doing barium venemas, you're doing lateral rectums, it happens with here. You've seen it with many laterals, it happens. You have more tissue than what you wanted. So all of this image here, all of this here, see, this was created by off-focus radiation, not by leakage radiation, and write this down, please. This image, and I want you to do this. I want you to do this. I want you to put an arrow here, an arrowhead. See, right at the nose. Boom, boom, boom. Arrow here. Okay, and said, this is not a scattered radiation, because it's a common mistake. Even senior techs will tell you, oh, that's a scatter. No, it's not a scatter. Okay, and I'm going to tell you one more thing. A scattered radiation, we're going to look at it probably in about a month in this class. A scattered radiation does not create an image at all. Scattered radiation will not give you, oh, look at that silhouette of, no, it will not give you anything. All scattered radiation will do is add fog, add darkness to the image, but not an actual image. So this is created by off-focus radiation. So what happens? So as I said before, you're going to have electrons going this way. They don't hit the target, and so you still make X-rays, and so you can have all of this is leakage radiation, right? If it's going this way, that way. But if that off-focus radiation is able to make it through the window, then it becomes off-focus radiation. Okay, and it gives you this, and it's not good. You probably, if you haven't seen it, it's because your computer is very smart, okay? Or the people that built that computer was very smart. All right, so what we have with what your DR system and your CR system will do is the following. they say, okay, see this dense area, we'll measure this. And so your computer mathematically knows that this is part of the image because it's dark. Okay, this is not part of the image, okay, because it's too light. Okay, and so what your computer will do is anything that is not within these dark areas, it will eliminate it, and that's how it comes up with the cones. It puts cones there, so you don't see it. Not cones, but collimation. And it closes. So probably that's why many of you have never seen this. But it happens with elbows, it happens with fingers, it happens with hands, it happens with everything, almost everything. Okay. Has anybody noticed that when the image is being formed, you see it, whoop, you see the shadow, and then whoop, it closes, and you don't see it. Everybody seen it?
Yeah.
Yeah, see, I'm not crazy. It happens. It happens. Yeah. Oh, you're at C, they still use CR, right? Yeah. It's easier to see it with CR, but it happens with DR too. You just gotta pay attention. Okay, has anybody else seen it?
Yeah.
You've seen it. Where are you? You're at?
The VA.
The VA? Yeah, okay. Do you see it with the DR?
Like sometimes the computer doesn't, I think it's the computer doesn't crop it right, and then we have to do it after.
You have to do it, and then you end up seeing this.
Yeah, so you see.
Yeah. Have you heard technologists calling this a scatter radiation?
No.
Oh,
I
good.
haven't.
No, good, I'm glad. Good. Guess it's not. Anything else about this? No? Fine. Good. All right. X-ray tube failure. X-ray tubes do fail, okay? And the most common reason is because of thermal, overheating the tube. And when you overheat the tube, either the filament cracks, but the anode, the target, can also crack or pit, and then you have to, it has to be replaced. Heat dissipation is a big problem, right? You know, and with all the ideas that have been put into play and to remove or to transfer heat from one side to another, you still have a big issue there, okay? Heat dissipation, you know, it can irradiate. It doesn't mean that it's radiation, it's irradiating to other areas. It's been emitted to other areas, it's just pure heat. Like when you are, you know, you get closer to a heater, right? When it's really cold, you get closer to the heater. You're not touching the heater, you're just getting it there, okay? By conduction, it means that it's being moved from one area to the other side, to another area. Convection is the same idea, but with convection, it goes through, you're using something to move it to another area. It's not a gap, it's not air, okay? That makes sense? For example, if you're moving it on a tube, like our heaters, you move it from area to area. It's through convection. Okay, all right. So, but remember that heat is a problem. And X-ray tubes, if you're using a tube a lot, you will get hot. It will get hot, guys. Okay, if you're doing multiple exposures. With fluoroscopy, it can get pretty hot. And remember, I don't know if I talked about, yeah, I did mention it to you guys, that be careful not to put any patient's body part on the X-ray tube. Oh, I think it was in Radt430, right? I was showing you a hip, and I said,
Yeah.
don't put the heel, don't put the calcaneus on the tube, because you could burn the patient. It happens. Okay, with all the heat dissipation you have there, you have the oil, you have the you have lead, you have metal, you might have even plastic. What they do, and let me go back here, just some of the things, some of the concepts that people have used to dissipate some of the heat. So oil is used, and oil is very effective, okay, in absorbing a lot of the heat. But also many X-ray tubes, and none of ours are like that, but some of the X-ray tubes, what they do is they have fans, and they are going all the time. They're blowing cold air. They bring cold air from the room, and they are blowing it to the X-ray tubes. Have any of you seen that? GE on their tubes, they use them a lot. They use it a lot. So they blow air, and then there are other things that they do is, for example, Siemens in their CT system. CT you can have an X-ray tube going at 140, 150 kVp, 400 mA, so you're using a lot of radiation, a lot of heat is created. So what Siemens came up with a few years back is what they do is they have all around the tube housing, they have these tubes, metal tubes, all around it. They almost encase the whole tube with these tubes, and through these tubes, inside these tubes, they run chilled water, like a radiator. They run this chilled water, and so that the water is move out of the room, and then you have a chiller somewhere, and they move the water, and so that's what they do constantly. Because in CT, you can have the tube going non-stop at the high kVp and high current that I mentioned. You can have easily, a minute. This thing's going non-stop, and so they get really hot. And so they use concepts like what I gave you, but it still is a problem. Okay, in CT, for example, average tube life is about 6 months. Yeah, it's about 6 months, and because it's so much heat being created, and heat is what's killing the tubes. Okay. Any questions about heat dissipation? No? Okay. Once again, just remember, careful. When the X-ray tube is going to be close to the patient, be very careful. For example, if you're doing weight-bearing feet, and you're going to put the patient's abdomen right next to the X-ray tube, don't have the patient hold the tube like this, because it might hurt. They might get burned. Okay. When I say burn to the point of them just going out, no, but it's going to get pretty warm. Now with the calcaneus, what I was saying when doing cross tables is because you're leaving it there for a while. Okay? You're not there holding it for a minute. You're there for 6-7 minutes while you're getting ready. So yeah, I will do it. All right, so let's just recap here. So the X-ray tube. The tube consists of glass envelope with an internal vacuum to encourage the free flow of electrons, right? That's what we want. Because if you have a gas, then the gas molecules will interfere, okay? And then it will be even more difficult to have the electrons go straight from cathode to anode. We already have the problem of having them the same negative charge, and so they repel each other. So that's a problem. And now you add gas to it, it's more problematic. The X-ray tubes contains a wire filament cathode, okay, that emits the electrons under the appropriate voltage. So here you run a high current, 5-6 amperage, to create all the heat. So you create that. And that when you change the voltage, when you make your exposure, is when the electrons flow. Right? Next, less than 1% of the kinetic energy of the incident electrons translates into an X-ray production. All right? Sounds familiar? All right, so 99% of all the energy invested goes into heat production, right? Yeah? Okay, good. The electrons are driven by a high voltage toward a tungsten target anode, here, okay? The target anode, okay, mainly tungsten. What else do you add to it, by the way? Radium. Why do you do that? Exactly, so stability, right? So you keep the tungsten attached to everything else, otherwise it will start just flying off because it's going too fast. Okay? All right, so 99% of the kinetic electrons are heat. The target itself must rotate to prevent overheating. All right? The whole idea, the whole concept we have in a rotating anode is that you have a larger surface area where the electrons can hit. Right, and there we go. See that? Good. All right, good. All right. Okay, rating charge and cooling curves. Okay. Many of the rating charts and cooling curves are already incorporated. You have on your panel, you have a microchip that already translates that for you, so you don't have to be looking at. You're still responsible to, if you have an older equipment, you might see a chart and you need to see it. Okay, you need to be able to read those charts or those curves. Okay, but for example, with that panel with our X-ray tube, you don't see a chart there. What you see is it gives you heat units. So when you warm, for example, if you're making a lot of exposure, it'll tell you you have 100% heat units available. And as you're making, the more and more exposures you make is going down. Okay, it's just telling you how hot the tube is, right? And you better slow it down if it gets too hot. For example, this semester we're gonna start doing some experiments there, and I'll tell you what are the heat units, and I'll tell you, oh, it's 10% or whatever. Then I'll say, okay, let's give the tube time to cool off. Okay, and so that's what the rating charts and cooling curves are saying. Okay, how hot it is. It's safe to make an exposure. All right, so radiographic rating charts, and we'll look at each one of them. Anode cooling curves, housing cooling curves, all of them are important. So here is an example of rating charts. So this is how you read a rating chart. Let's concentrate up here. Let's look up here, guys. What this chart is saying, look at the information that is being provided to you. So the anode is rotating at 3,400 RPMs. That's one thing. So it's not a very fast tube. Okay, anode is rotating, relatively speaking, slow, right? Compared to this one, for example. This one is going at 10,000. This is telling you 1 omega is what?
Phase.
Phase. So it's one phase, okay? And it has 0.66 millimeters of the focal spot, okay? Of the filament, I'm sorry, and then 11 degrees. That's how much angle do you have on this tube. Okay, so there's not much. Okay.
On the target?
On the target. Now, let's take a look at what the MA stations do. So you have 200 MA station, 150 and 100. Okay? So, as you can see, so anything below here, anything below the green line, you're safe. Safe in what? It's not hot, it can take this heat. Anything above this, using 200, is not safe. The same thing here. Anything below this line, this light blue line, is fine for if you're using the 150 MA station. Are you following me? Okay, and the same thing here. Anything above that dark blue line is not safe if you are using the 100 MA station, but anything below that, including any area below the dark blue line, is safe if you're using the 100 MA station. Also depends on the kVp. So let's take a look. For example, let's think about, okay, I'm setting up my panel and I'm gonna say 200 MA station. Okay, that's what I want to use because I want detail. So I want to use the small focal spot, right? 200 MA station. Okay, and I said, oh, okay, let's use. How about if we use, I don't know, 75 kVp? And so we'll take a look. 75, and what do I say? 1 second, right? Yeah, let's say 1 second. So this is my line here. Is it safe to use 200? No. Why? Because I am above the 200 line. The tube is going to get too hot. The tube is compromised. Okay, you can't use it. The tube will not allow you to use it. But even if you try it, some of the older equipment will allow you to do it, but it's not safe. You have a great chance of cracking that tube. Let's use 0.1. Okay, can we use 0.1 at 75? It's right on the line, maybe a little bit above. I wouldn't use it. So what I need to do is I can bring the kVp lower. Maybe you can bring it down to 70. Okay, at 0.1, yeah, that will work. Okay, let's look at one with 100. It says safe to use 75 kVp at 1 second if I'm using 100. Take a look where I am. I'm here. So I am below this line, so it's safe. But it will not be safe if I'm using 0.1 and 150 kVp. Then I am not safe. Okay, is it clear? All right, let's do another one. Let's do this one with a lot of lines. Okay, so once again, here we have, this information is important. What this is saying is we have an anode that is rotating at 10,000 RPMs. So it's fast. So just that is telling me this is, I'm gonna have better heat capacity. Okay, next is telling me there is a 3-phase, okay, a 1 millimeter filament. So I know it's large. Okay, and it's telling me that is at 11 degrees. So it doesn't change. So it's telling me it's just one area. Okay, that is not gonna change. What is gonna change is probably the filament. All right, so now here you have a whole bunch of lines. Take a look. You have, for example, you have the 250 here, 300, 400, 500, 600, 700, 800, all the way up to 10, all the way up to 1000 MA. Okay, so now let's take a look. If I am using, say, a common MA, I like to use the 400 MA. Okay, I was told when I went to school that if you use the 400, it's pretty safe to use it. You can use a lot of mass if needed. So anyway, so let's use the 400 MA. Okay, so it goes here, right? So if I am using, let's say, 1 second, and let's say 100 kVp, that's a lot. Okay, that will give me 400 mass. Okay, and 100 here. Is it safe? Yes, it is. If I'm using them. Okay. Now, if I want to go to, let's say, 130 kVp and using one, I am not. So, once again, it's very simple. Get familiar with this charge. Anything above is not safe. Anything below the line is safe. Yeah.
Does the anode change speeds, or just the tube has a different speed anode?
Tubes have different speeds. Yeah. Yeah. No, that doesn't change. Yeah.
It's going to be constant.
Yeah, it's
depending
gonna
on
be
the
constant.
tube.
That would be cool, huh? Being able to change that. Gears. I think it's a good time to take a break. They already lost a minute. Take a break. Yeah, come back.